All right, we continue the examples. We have the flashcards right next to us. Let's look at example number 9. Okay. Obviously, we cannot do direct substitution. We cannot do quotient rule, quotient law. And the obvious choice is rationalization, rationalizing the numerator, right? So the conjugate of the numerator. So we just change the sign to plus, the two roots subtracting or plus, and that makes a conjugate. And we apply mathematical principle number 1. And this makes 1, so anything times 1 stay the same. So we applied mathematical principle number 1. You can see these mathematical principles that we use in algebra, very, very useful. Okay, we continue to use them. So after we multiply the conjugates, and the next step, we're going to take a denominator times denominator, numerator times numerator, but numerator times numerator, we're going to bring this conjugate thing with us, right? We're going to bring the conjugate thingy with us for our convenience, right? So this piece multiply that piece, right? Multiply these two pieces, and what do we get? We get a squared minus b squared. So a squared, this is a and this is the b, right? So you can, so now we're gonna focus on doing a squared minus b squared. All right. And once again, we have these issues we talked about before, right? And just in case, right? So the first one does not apply, the second one does. So we're gonna keep going. Okay, so this piece equals just 1 plus t. And the latter one is going to be 1 minus t. Okay, so I'm being very careful. I put a little parentheses there, 1 minus t. If you want to open this parentheses, because here it's very, very easy to make a mistake. It's very, very easy to make a mistake because people can just do this. And then you're doomed. Okay, so I'm being careful. I put parentheses around it. If you are in such a hurry, right, and open up the parentheses, remember this is going to turn into plus t. Okay, you could save this step. You could make this optional, but I would not, because this kind of practice, I consider is a good practice. When you have parentheses and there's negative sign in front of parentheses, to write that one extra step. And it makes it easier also for you when you have time to come back to check your work. Okay, so that's a practice I encourage you guys to consider adopting. So now I got 1, 1 minus 1, so now I have 2t. So now I can be more liberal, right? And t reduced, right? On my next step, I reduce the t, no more t. Can I do direct substitution? Yes, we can do direct substitution right here by replacing t by 0. Or you say, hey, I like to use a limit law. Limit law looks nice, right? So you can put these limits and bring them in here. You see this sometime in the textbook. Some textbooks they will, in order to show you the application of limit, they even put it here, right? because this will allow you to use all the limit laws. And that's okay, no problem. Okay, so next is just basically direct substitution. So this is so now we can direct substitution. So I'm going to remove all of these. T is going to be substituted by 0, 0, and this is going to be gone. I don't need them. And this equals to 2 over 2. That's going to be equals to 1. Okay, so if you like to write it this way, hey, why not? Okay. So that was the question we just did, right? So that's the complete question. So yes, some of the steps are optional. Okay, some of the steps are optional. I encourage you to show your best work, to make them organized very well. Yeah. Let's look at number 10. Let's look at number 10. Look at number 10. Number 10 on the first side, as we can see, t approaches 0, right? We have a 0 in the denominator in this case. We have a 0 in the denominator in that other case. Obviously, t equals 0 is not in the domain. We cannot do direct substitution. And so here, I'm going to put a think out aloud. Right? Then the first thing you'll be thinking, can we apply limit law? Right? To apply limit law, the individual limit must exist. And they'll be checking, does this limit exist? 1 over t, and then it does not. Right? And how about the other limit? Right? How about the other limit? Does it apply? No, they don't. Right? So if you look at the limit law, they don't apply. So limit law, so both limits, they do not exist. Oops. Okay, let me use. They do not exist. In fact, if one of the limit does not exist, you cannot apply limit law. So we cannot apply limit law. So limit law do not apply. And then what can you do? Then what can we do? Right? We will have to resort to algebraic manipulation. Okay. Let's see, how do we manipulate this algebraically? Well, I'm thinking I'm going to factor the t. Okay, I'm going to factor out the t. Okay. Factoring out the t, I'm going to get a t times t plus 1 in the denominator. And then I also noticed that this letter form can be written as this. 1 over t plus 1. Right? If you multiply these two, you're going to get back there. Then I realized that 1 over t is a common factor. How about I factor that out, right? You will see that factoring is a very common practice, and sometimes factoring make our life it's just a little bit easier. So I'm going to factor out 1 over t. After 1 over t is factored out, I get 1 minus t plus 1. T plus 1. And after this, let's see if we can make a common denominator. At this time, can we use the limit law? The answer is no, because this limit does not exist. And if one of the limit does not exist, you cannot apply limit law. period. So now we still have to move forward to take care of the common denominator, but this work certainly made the common denominator process a little bit easier, right? So I'm gonna 1 is equals to t plus 1 over t plus 1, subtracting 1 over t plus 1, right? We got the common denominator. Some of these steps you can do it on scratch paper, but I'm just doing it here. So we have the same denominator. So numerator subtracting numerator. So this is going to be -1. So this is gone. And now we got this reduced. And parentheses can be removed. Oh, t and p can be reduced. P and T are reduced. Whoa, we get something really nice. Now we can apply limit law or direct substitution. I would just do direct substitution here. And we're getting 1/2. Right? You can see, now we look back, this question is seemingly pretty awkward. But after we patiently work with it, we end up with the answer like pretty quickly. Okay, but from this example, you also see that, both limits do not exist, right? And when you subtract them, and we do have a limit. Remember, there's another video we talk about that if two limit doesn't exist, right? You subtract them, do they have limit? Or you add them, do they have limit? They may. Okay. All right. So let's look at the next one. All right. And so this is another situation that limit law does not apply. Okay. And we also have radicals, but inspired by the previous question, right? So I'm going to rewrite, because I'm all for simplifying as much as I can. Because if I can simplify, my life will be just so much easier. So the first one, right? So I want you guys to see this as the first part as 1 times 1 over root. Okay, these two are the same. So I can factor out the 1 over t. I take out the 1 over t. Okay. Factored out. And this 1 over t is also factored out. So it becomes 1. And you can verify if you just take this one, multiply that, you go back here, you take 1 over t times 1, you're going to go back there. So everything's justified. And then what do we do? T is out, and we're going to have to find common denominator, right? So what is the common denominator? The common denominator is the root of t plus 1. The root of t plus 1. And then what do we do? We're gonna get the common denominator, and we do 1 minus, we keep the common denominator, right? And we do 1 minus that, oops, what am I doing? 1 minus the square root of t plus 1. So this piece is gone. I can also remove the parentheses. Okay, I can also remove the parentheses. You don't have to you can put a dot there, or you don't have to. Okay, but if you write it that way, it's okay. Now we get a root. We still cannot apply limit law. What do we do? Rationalization. The conjugate of that piece, okay, is 1 plus. So we're going to multiply by 1, principle number 1. Anything times 1 stay the same. So we're going to do the conjugates. Okay. Denominator times denominator. So this piece times the denominator over there. I want to tell you, don't try to multiply this, okay? Just keep it this way, okay? Keep it this way, and you're gonna like it, okay? I promise you. And now this piece times that is a minus b times a plus b, so we're gonna apply that a squared minus b squared, so it's a squared minus b squared. Boom. All right. And the next step, I'll keep everything in place. Keep everything in place. Denominator, no change. And then 1 squared is 1. And the square root of b plus 1. And so once again, right? So let me, this piece applies. Okay. So I'm just going to copy here just in case. Right there. Okay, that's where it's useful. And that piece is useful. You know why already. So this piece will give us t plus 1. I'm going to be very careful. E plus 1 in parentheses. Then I'm going to open parentheses on the next step. Okay. 1 minus t minus 1. 1 minus t minus 1. And 1 minus 1 makes 0. So we get to have a negative t left. And this t, take away this t, reducing, because t is not 0, even though it approaches 0 by intuitive definition of limits. So this t is being taken away by the other t. By this time, we can just do a little trimming. Can we apply limit law now? The answer is yes, we can apply limit law now. Okay, because no concern about limits, no concern of 0 denominator, and limit, every individual limit we are going to take limit of exists. The constant, the limit of a constant is still the same, right? Now we just substitute. The top is -1. The bottom is just, this is going to be root. You can see we don't, now you understand why I didn't multiply them. No need, right? So to keep it as factor form doesn't bother anybody. And so over here, you're going to have 0 plus 1. You can even omit this step. So by this time, you already have the answer. The answer is -1/2. -1/2. Okay. Yeah. So let's look at number 12. Number 12 is very similar to the work we've done. Of course, there's some nuances. And you may like to pause this and try by yourself. On this example, number 12, you can see we still cannot use the properties of limit laws, and we cannot use direct substitutions either. Because x approaching -4, x plus 4 is going to be approaching 0, or -4 is not in the domain of the function. So we cannot apply those nice properties. So once again, we're going to rationalizing the numerator. Okay, so the conjugate of the numerator will be the root plus 5. And we're going to create number 1. 1 times anything stays 1. And then we're going to continue to finish up the multiplication. the denominator times denominator. So once again, we're gonna take the denominator here to multiply x plus 4, and don't multiply this out. Just leave it as is in the product form, and the numerator times the numerator, and we're gonna get a squared minus b squared. So this piece is gonna be squared. Oops. Squared minus 5 squared. So that piece is gone. And the next step, we're gonna simplify. Okay, keep the denominator as is. And the top, right, is gonna be x squared minus, x squared plus 9 and minus 25. And that will give us the next expression, which is minus 16. X squared minus 16 can be factored, and that will give us x plus 4 times x minus 4. And x plus 4 is not 0, so we can reduce it. So the next step, we're going to get a reduced form without the x plus 4 in the numerator and denominator. And now we can directly substitute, or you can apply limit law. I would just directly substitute, replace x by -4, and replace x by -4. You can see by this time the limit is already dropped, because as soon as we do the direct substitution, let me bring back where's my direct substitution? There. Yeah, you can see on the direct substitution, the limit symbol doesn't show up on the right-hand side. Okay? Simplify the bottom, right? We get -4 squared is 16. 16 plus 9 is 25. The root of 25 is 5. And so this piece is going to be 10. And the top is -8. Reduce it is going to be -4/5. Right? Let's look at number 13. Complex fraction. One more time. And we still cannot apply limit law because denominator can be 0 if we substitute, right? So we can't do that. So we're gonna apply the algebraic skills. The common denominator is x squared multiply x plus h squared. So we multiply by 1, right? So we created 1, and we take the numerator. We take the numerator to multiply the numerator on each term. Distributive law. And this piece, we're going to take it to multiply the denominator. So numerator times the numerator, denominator times denominator. Reducing x plus h squared reduce, so get x squared over here. X squared times 1 over x squared, that's equals to 1. Don't do anything with the denominator. So we have reduced it. So the next step, we're going to simplify. What do we get for simplification? Right, let's see how we simplify. You can FOIL this and do multiplicate and then simplify. But I'm going to show you a slightly different way from what you might do. I'm going to factor these. Okay, I'm going to use a squared minus b squared. They reverse the direction from right to left to accomplish this. Is there any particular reason? No, there's not really any particular reason. It's just from left to right. They just, show you how algebra can be done, in a certain way. So our A is X, right? Our B is X plus H. So you can see we're gonna, this is done on my sketch paper, okay? So I'm gonna put this as think out aloud. Okay. So I will get A plus B times A minus C. So A is X. So A is replaced by X. B is X plus H in parentheses. So B is replaced by X plus H. Boom. Boom. Right? So that's what I'm getting for that piece. Okay, just reduce it. And the top is on this parentheses. If you like, you can make it bracket to see it, to make it see better. Okay. And you can make this other one bracket. Okay. And so this piece is just going to be, I'm going to simplify. I'm going to simplify. The first bracket is just X plus 1 plus X plus H, right? That's it. The next one, oh, wait, it's not a 1, it's X. My bad. This is X. My bad. All right, sorry about that. Okay, so this is X and this is X. Sorry about that. But anyway, so the first one is going to be 2X and the latter one is X minus H. So this is going to be negative H. Okay. And this negative H is going to take away the H in the bottom. So reducing the H will take away this H. So reduced. So near the end, let's see what we get. So this is a -1. So I'm going to put the negative sign in the front. H is gone. So we no longer have that situation that may cause the denominator equal to 0. So the next step would just be a direct substitution. Direct substitution, substitute H, okay, because we're taking limit on H. So in the end, we get negative 2X over X raised to the power 4. And reducing it, we get a negative 2 over X raised to the power of 3. Okay. All right. So that's that's example number 13. We're going to move on to number 14. So by this time, you may like to take a break and come back and try number 14. You can pause the recording. For number 14, you see, it looks a little bit different. We have X approaching 16. And, well, if we factor the denominator, you will find that 16, well, if you plug in 16, it's not going to work, right? It's going to make 0. So we're going to factor out the X. We're going to factor it out an X. I put it outside. And then what do we do? Right, we have a 4 minus root X, and X is approaching 16. We can't use any direct substitution nor limit laws. So we have to do something algebraically. Well, since x is approaching 16, we can assume x is positive. If x is positive, what we can do is that this x can be written as root x squared. Oops, whoopsie, sorry. So this x, right? So basically we're using this, okay? I'm gonna show you what we use. This piece. Okay, we're actually gonna use this piece. In other words, x is equals to root x squared. And because x is positive. Remember, there's a domain issue, right? And 16 can be seen as 4 squared. Okay, so it's a squared minus b squared again. And we're going to factor the denominator. So we factor the denominator, so it's a 4, as a factor, we use this piece, right? So we use that piece. Let me bring it over here for our reference. There. All right, and so this is a 4 squared minus root x squared. We're going to factor this, and it's going to be factored into 4 minus root x multiply 4 plus root x. All right, and after this factorization, 4 minus root x and 4 minus root x, they're not 0, they will be reduced. There. Now we no longer have the issue of a 0 denominator, and we can apply limit law now, which is going to be equals to, if we apply limit law, okay, you can write it the following way, right? You can take the limit and to take limit on x and take limit on 4, but limit of 4 is going to be 4. So you can write it that way. The limit of 1 is 1. So we basically use the product, addition, subtraction, and there's no attraction division, right? So the quotient rule also apply. In the end, we will get in the denominator, or the numerator is just 1. Denominator here is going to be 16, limit law, multiply, and the root 16 is 4, 4 plus 4 is 8. Okay? And what does that equal to? Just multiply 16 with 8. So it's 1 over 128. 128. Finished, right? So you see various form, but the technique we use is pretty common. In the following example, right? So I got to renumber them. This is 16. In question number 15, we look at 2 limits. We're going to do 2 limits mainly for the comparative effect. We know that this is nothing to be reduced of, but if you look at the picture, if we look at the picture of this function, right, we have the same function. Obviously, at 5, it's undefined. Right? And so make this maybe 6. All right. So x equals to 5 is the vertical asymptote. It's a vertical asymptote. And with that consideration, as you can see, the limit, depending on where we approach it, right? Approaching from left or right of 5, it makes a difference. So 5. Okay, I'm just drawing these vertical asymptotes. All right, and let's see more of the graph. I'm going to put 20 there, right? So there's another piece. We're going to make it just a little bit more. Okay, so on this side we can make it -1. So I just want to adjust the picture so we can see better, especially in the neighborhood of 5. So we look at these two limits, right? The first one is talking about as x approaching 5 from smaller than 5. So we're approaching 5 from smaller than 5. And it approaches negative infinity. The other one, oh no, sorry. This one is approaching 5 from smaller. So the limit is going to be negative infinity. And the other one approaching 5 from larger than 5, right? So that's going to be approaching positive infinity. So this is going to be positive infinity. So that's how these limit, right? Then you see if I don't take a picture, if I don't draw the picture, then I cannot tell. Well, we can still tell. So here I'm going to write up a couple of things to show you. Okay, I'm going to switch up place actually. Let me switch up place so you can see the correspondence better. Okay, I'm going to switch to this piece because this is approaching from right, and this is approaching from right. This is approaching from left, and this is approaching from right. So I'm going to put this one over here, right? So this piece corresponds to this branch, and this other piece corresponds to this, the right side branch as x approaching positive 5, as x approaching 5 from smaller, which is this side, and x approaching 5 from larger. So you say, well, if we don't see the picture, can we still draw the conclusion properly? And the answer is yes. How do we do that? Okay, how do we do that? And first of all, we understand as, take this piece for example. Okay, take this piece for example. Without seeing the graph, right? And when we analyze this, you see as x approaching 5, the numerator is approaching 6, but the denominator is approaching 0. So I'm going to write it up for these analysis. Okay, so you can say as x approaching 5 from smaller than 5, right? Then x minus 5 is approaching 0 from smaller than 0. Denominator approaching 0. And the numerator, right? Numerator, x plus 1 is approaching 6. So the numerator approaching a finite number, the denominator approaching number very, approaching 0 from smaller than 0. And of course, this is going to be, the limit is going to be negative infinity. And the same thing is true for the other one, right? So you can analyze that way. So similarly, in similar manner, you can say as x approaching 5 from larger than 5, right? X minus 5 is approaching 0 from larger than 0. And of course, X plus 1 is still approaching 5. Right? So in the end, of course, this is going to be approaching positive infinity. So that by breaking it down, we can justify it that way. The following examples, and I'm going to show you how we, utilize the sign thing to analyze. Okay, so I'm going to bring the sign analysis, right? Mathematical principle number 6. Mathematical principle number 6. How do we analyze, situation like number 16? Okay, so we're gonna come back to correct the other numbers. Okay, so as x approaching 2, right? And obviously there's nothing we can reduce. You can expand it, there's nothing you can reduce or cancel, right? As some of us like to say. But we can't reduce anything, so we're going to resort to analysis. Here, I'm not going to draw the picture. I'm going to draw the picture after to see if our analysis makes sense. Okay, so as x is approaching 2, as x approaching 2, x minus 2 is going to approach 0. And is approaching 0, it is also positive, right? And the numerator, x squared, is approaching 4, right? So a number approaching 4 in the numerator, denominator approaching 0. And of course, this is going to approach positive infinity, right? So now, if you're not certain, I'm certain already. And this analysis, if you want to see the picture to confirm, right? To confirm in the neighborhood of 2, and you get this picture, right? Then the whole thing is going to be positive for sure. Okay, the whole thing is going to be positive because you have squared in the numerator, square, something square in the denominator. So this piece, right, you can see is going to approach a vertical asymptote. So we have a vertical asymptote. So there's a vertical asymptote there. So our analysis earlier was confirmed. Sometimes, we need to know how to analyze. Okay, we need to know how to analyze, but we also need to, in the case that we want to confirm our analysis, drawing a picture, which is not difficult these days. Okay. The next two questions are related to familiarity with the function, with certain function. X is approaching pi over 2 plus, right? If you're not familiar with secant, we can rewrite it as it's at the reciprocal of cosine. So it's 1 over cosine x, right? And obviously, as x approaching pi over 2 from bigger than pi over 2, this number is going to be fixed. There's nothing we can reduce. So what happens if cosine is approaching, cosine x approaches what? Well, x is approaching pi over 2 from larger than pi over 2. Well, we are familiar with cosine curve. You can look at it this way. Okay, cosine x. Cosine x, we know that Oh, wait, how did I get this picture? Cosine. There. All right, I don't know how that picture came to our view. That was a mystery, but never mind that. So we're going to look at the neighborhood of a cosine. Okay, pi over 2 is right here. Pi over 2 is right here, right? So let me mark the point pi over 2. Pi over 2. Pi over 2, comma, 0, right? I'm just going to mark that input on the graph right there. And when x is approaching pi over 2 from larger than pi over 2, obviously cosine x is approaching 0 from smaller than 0. You see, because x is larger than pi over 2, right? So let's write it down over here. So as x approaching pi over 2, from larger than pi over 2, this direction, cosine is approaching 0 from smaller than 0. So this piece is negative. And this piece is a finite number, right? You know, pi over x approaching pi over 2, 1 over x approaching 2 over pi. Okay, we can also write that as x approaching pi over 2 from larger, 1 over x is going to approach 2 over pi. Okay, because it's the reciprocal. So it's a finite number. It's a finite number divided by something close to 0, but negative. So this limit is going to be negative infinity. Well, it doesn't have a limit. It's negative infinity. Okay, it's negative infinity. So that's how you analyze. It requires some knowledge of the basic functions. Okay. So that's how we analyze that. In case that algebraic simplification is no longer available to us. Number 18. 18 is also requiring us to apply the properties we know about sine. For example, sine x is in consideration. And we know the sine curve, right? Everybody knows the sine curve, but we're interested in the behavior of sine in the neighborhood of 0, and especially on the right side. So we're only interested in on this side, not the other side. So here's a sine curve. So when x is approaching 0, right? So as x approaching 0 from larger, x is approaching 0 from larger, right? Sine is approaching 0. It's also positive, this piece, right? It's going to be approaching 0 from larger than 0. Now, sine x is approaching 0 from larger. ln x, we need some familiarity with ln x. Okay, ln x is a curve like this. We should be pretty familiar with ln x. Okay. So when we combine these two functions, the basic graph, then we will have some idea. ln x. So here's ln x. Okay, we're going to bring them side by side. We're going to bring them side by side. So I'm going to bring this piece to over here. Now we're going to see a little bit better by analyzing these two curves. All right, so this direction is negative infinity. So you can see as x approaching 0, from larger than 0, find x approaching 0 from larger than 0. That's in the domain of ln x, right? So as this piece is approaching 0 from larger than 0, so first the x approaching 0. So now sine x is approaching 0 from larger than 0. And logarithm, natural log of something, and that's going to approach negative infinity. So that's where the curve goes down to, right? So the conclusion is going to be, this is going to be negative infinity. This is going to be negative infinity, right? So this requires us to be familiar with these two basic functions, all right? Okay. Let's look at number 19 and 20. This is 20. Oh, did I prepare so many? All right, 21, 22. I don't know how much time has passed, but anyway, so let's look at 19. 19. Okay. For 19, we certainly try to reduce. We cannot apply limit law because the denominator, if x equals 1 is plugged in, it's going to be 0. So we can't apply. So we're going to factor. So the numerator is going to factor into x times x plus 2. The denominator is going to be x minus 1 squared. Oops. X minus 1 squared. Sorry about that. Okay. But then there's no common factor. We can't reduce anything. We cannot reduce anything. So you can see the numerator, right? So as x approaching 1, then x minus 1 squared is going to approach 0. Larger than 0 because it is squared. The top is approaching a finite number. It's approaching 1 times 3, that's 3. So the top is approaching a finite number, denominator approaching 0, but positive. So the limit is going to be positive infinity. Okay, you can draw the picture to confirm it, right? You can draw the picture to confirm it. And if you have any uncertainty using the tool, using graphing tool, it should be helpful. Okay, it should be helpful. And you can see at 1, near 1, right? There's a vertical asymptote. There's a vertical asymptote. All right, 20. Okay, I think we already did this question. I could remove that. Okay. 22, I think let's finish this one because the next one is going to be too short. Okay. So it should be done by, we should be done not too long. Okay. 20. 20 involves two functions, right? 1 over x, we're pretty familiar with 1 over x, but x is approaching 0 from greater than 0. I'm going to bring back our logarithm, ln x, right? So we're going to bring ln x with us so we can use it. So this is ln x, and this is 1 over x, x approaching 0. And as x approaching 0 from larger than 0, right? 1 over x is approaching positive infinity. right? 1 over x is approaching positive infinity because the denominator approaching 0 when larger than 0. How about ln x? At the same time, ln x is approaching negative infinity. Negative infinity. Okay. So infinity minus negative infinity, so the whole thing is going to approach, the whole thing is going to approach positive infinity. So that's the limit. Okay. Number 21. As x approaching 0, right? As x approaching 0, we can't reduce it, really. We can't, and x squared is approaching 0 from larger than 0. Right, then we're still familiar with, natural logarithm curve. So this piece is approaching negative infinity. And this piece is approaching positive infinity, right? So this piece is approaching positive infinity. So this is negative infinity, this is approaching negative infinity, this approaching positive infinity. So this is just going to be negative infinity. The whole thing is going to approach negative infinity. Okay, there's simplification. You can try simplify. It's not gonna make it. It's not gonna make it. Okay, maybe I'm going a little faster. All right, number 22. Number 22, if you try to factor, most likely it's not gonna work. I'm sorry. If you try to use the limit law, it's not gonna work. Okay. So you can pause and try that. And what we need to do here, I'm going a little faster because I don't want to make this too long. So we're going to factor the top is going to be x minus 4, x minus 2 squared. The denominator is going to be x squared minus 4 multiply x squared plus 1. Okay, that should be the factor. Further factoring, right? X squared minus 4 can be factored into, let me get right, one more step. Okay. That can be written as x minus 2 times x plus 2. All right. So by this time, we can reduce the x minus 2. Okay, so all the narratives are applicable. And here we go. Now the denominator is no longer 0. We can do direct substitution at 2. Right? So remove this and replace x by 2. The numerator is 0, so the whole thing is 0. Denominator is not 0, so the whole thing is 0. All right. Number 23. Number 23. Number 23 is a complex situation, complex fraction. And of course, we can't apply limit law nor direct substitution, but we need to remember how do we express it, right? So it's really, this piece is really just means the 1 over negative 2 plus 8, and this 1/2 is for 2 to the power negative 1. Common denominator, right? So I'm going to have 2 times negative 2 plus 8, right? So we'll multiply by 1. So we create a 1. And we take the numerator to distribute to each piece. And multiply that, half. And this denominator multiply the denominator there. multiply. Okay, simplify and continue. In fact, you can work on that. So this piece is going to reduce with that. So we have 2. And it's half times 2 is 1, right? So you open parentheses, we got that, right? 2 minus 2. And almost there, because this has h left, h and h reduced. Boom. So we can do direct substitution. We can do direct substitution. So in the end, we just do direct substitution, replace h by 0. So equals to -quarter. Finished. 2 more to go. 2 more to go. These 2 questions actually were, covered before in a slightly different setting. We're going to do it anyway. But here, we're going to utilize the piecewise function alternative for absolute value of x. Okay, of course, we are aware of the domain for sure. The absolute value of x, right? The 2 cases. The 2 cases. So if x is greater than or equal to 0, and the absolute value of x is the same as x. If x is negative, the absolute value of x is the opposite. We utilize these 2, okay? And let me move forward this way. All right. Put this, we're going to apply this piece. When x is approaching 0 from smaller than 0, right? The only part we need to handle is absolute value of x. If x is negative, this absolute value of x is negative x. Okay? And that equals to 1 over x minus 1 over negative x. That's going to be, whoops, my bad. Okay, so I'm going to copy this. So basically, this is a plus 1 over x. And that would, combining the like terms, that's going to be 2 over x. Remove the parentheses, x approaching 0 from smaller than 0. So this is going to be approaching negative infinity. The next one, we still apply the same property, which is going to give us the limit, right? As x approaching 0 from larger than 0, so absolute value of x is going to be positive because x is approaching 0 from larger than 0. And that piece is 0, right? 1 over x minus 1 over x, that's a 0. The limit of 0 is 0. Okay, so all the questions in our plan have been covered, 25 questions. Many of them are from your homework, okay? I recommend you guys, work along my side and then try to do it on your own. Thank you for watching.